Thank you. Good morning, and thank you, Jeremy, for that reassurance that I don't need to get through this in 10 minutes. That's quite a relief. The theme of the day is Palaeoinformatics, but I'll come clean and say I'm not going to talk about that. I'm going to talk about bioinformatics. I'm talking about using present-day databases to illuminate the past. So that's possibly a reasonable thing to start the day with anyway, I think. Where do I point this to make it go forward? Oh, it's going. Okay, we'll get there. So, yes, right. We'll start again. So, this began for me, my interest in databases began with the NODE database, Nonmarine Ostracod Distribution in Europe. This is a GIS database of living and fossil, quaternary at least, ostracods, freshwater ostracods, and it came out of a European Human Capital and Mobility Programme project on the evolutionary ecology of reproductive modes in non-marine ostracods. Essentially, we wanted to map the distribution of sexual and parthenogenetic reproductive modes across Europe. We could have done it more easily and quickly on paper, but we made a decision early on that we wanted to do it electronically, mindful of future possible applications of a database if we started building one. It took us almost half of a 3-year project to even get to the point where we could begin to map things, but it's paid off because all this time further on from that project we have something that is still being built, still being improved, and is proving very, very useful for various applications. In case you don't know, ostracods are microscopic crustaceans. They have a calcareous bivalve shell. They're very diverse. They're widespread in practically every kind of aquatic environment, marine and non-marine. They have an excellent fossil record because they have calcareous shells, go right back to the Ordovician, and they're extremely valuable as paleoenvironmental proxies. And an example of their use is something that I've developed, which is the mutual ostracod temperature range method, or the motor method as we call it. It's something that reconstructs past air temperatures from the modern climatic distribution of non-marine ostracod species. And it determines the mutual ranges. The example here shows you what we do. We have calibrated species ranges. You've got a temperature scale along the bottom of the graph here. Calibrated species ranges based on the modern distributions of the species are basically lined up for a fossil assemblage, and then we fit a temperature range as closely as possible to that shows us the temperature range within which all of those species could have coexisted. We do it for July for summer and January for winter, and comparing that to present day temperatures, you can see that the present day July temperature falls within that bracket, but in terms of the January temperatures, the reconstructed paleotemperature, this is for a Pleistocene Hoxnean or stage 11 interglacial, actually falls at least a couple of degrees below the present day temperature, suggesting a more continental climate compared to the maritime or oceanic climate that we enjoy in Britain today. Well, I'm not sure if enjoy is the right word. Look at that. So there are two particular things that we need, two essentials for calibrating the living distributions of ostracod species for such paleoclimate reconstructions. One is the database of living distribution, so the upper diagram, which is showing you various databases around the world, which I'll say more about in a little while. And we also need modern climate data sets against which we can calibrate those distributions, because we're not so interested in their distribution in geographical space, we're interested in their distribution in climate space. So here's one example of how we calibrate a species. This is a freshwater ostracod species called Prionocypris zenkeri, being calibrated for the motor method. And essentially what we do is map the distribution in, this is using the NODE database, and then using a climate data set in a GIS, we are trying to fit as tightly as possible a temperature range for July and then for January that will enclose all of those records, and we end up with a mean July temperature range of +14 to +26, January -4 to +6. And we've done that now for about 70 or 80 species that are fairly common in Europe. Now, what are the needs? What kind of databases do we need to do these kinds of calibrations? What is really suitable? Small regional data sets can be really impressive. Those that are collected perhaps during a relatively short time, perhaps even in 1 year, by a group of people or one person working consistently. They can be internally consistent in terms of sampling methods, the taxonomy, positional accuracy and so on, but they tend to fall short of capturing the full climatic or temperature ranges of the species that we're interested in. So they're of limited use on their own for paleoclimate reconstruction kind of work. The example shown here is a fantastic data set from Mongolia, all collected in July 2008 by Tess van der Meren and his associates, and this is just showing some of the records that he's provided for a metadatabase I'm going to explain about in a moment, mapped onto Google Earth here so you can see where these things are. So we need larger data sets, we need larger databases. So Node, that I've mentioned already, is a larger data set. It covers pretty much, well, it's got a good coverage of Europe. You can see there are some gaps. You can see that we have a fairly broad view of what constitutes Europe as well. We're moving down into North Africa and so on. But it has getting on for 10,000 living records, maybe 2,500 fossil records now, quaternary ones. These are all from the literature. So the dates of collection are spread over about 150 years. We've got a lot of records. It's a pretty extensive database. And as I say, it includes fossil records. If we move across the Atlantic, we have two really big, fantastic databases. In Canada, we have the DODE, which is to rhyme with node, the Delorme Ostracod Horticological Database. And I should perhaps point out that the spelling of ostracod or ostracode is kind of optional depending on which side of the Atlantic you were born. It's an enormous database, more than 30,000 records, more than 6,000 sites. It has a huge amount of environmental data with it. And just to give you some idea, you can't really appreciate the density of records from the yellow dots there. But if I blow up one part of it, you can just see how good the coverage is. And yet, these are the accessible parts of Canada. So there's been a particular effort to get some up here in Arctic Canada, but there's really a huge amount of space untouched. If we look to the south, and just note that database absolutely finishes along the US border, then we have a USA database called Nanode, more than 2,500 records, collected mostly in the late 20th century, lots of environmental data, particularly water-solute chemistry data, extremely useful. But even these databases, on their own, have their limitations. So all three, Node, DODE, and Nanode, sounds good, doesn't it? We're going to be hard-pressed to find good acronyms for the remaining databases, for the remaining regions, I think. All three of these have been used individually for paleoclimate reconstructions and various paleoenvironmental applications. But do they, on their own, capture adequately the geographical and most importantly the climatic ranges of species? And the answer is no, they don't. First of all, ostracods don't respect political boundaries, fairly obviously. So you have that, if you look at the Canadian data set, you have that line across there, which is the US border, and you have no records south of that. This is a comparison of calibrations of one species just for the July temperature ranges. And you can see, even if you don't look at the numbers, you can just see from the yellow pattern, which is the mapped temperature range, that there are some differences there in North America. You get different answers depending on which data set you use. And this is an ostracod species that does live on both sides of the Atlantic. So it just happens that the nanode data set does capture, if you combine them, you get +11 to +30, and that's what the nanode database gives you. Although it doesn't extend as far north as the Canadian one, it compensates for that by having some higher altitude records, which can give you some of the lower temperatures at the lower end of the range. And if we compare not just the July but the January as well, you see it a bit more clearly. So here we have the Canadian data set. These are the calibrations. Here's your temperature scale. Here's the Canadian data set, the USA data set, the European data set. And if we do a combination of all three, we get a better capture of the temperature range of this species. And just as a little aside, here's an ostracod that does apparently respect a political boundary. This is a thing called Candona acucula. Here's its distribution in the Canadian data set in Dode. It's pretty common across the sort of Midwest there, but it doesn't occur at all in nanode, in the USA database. And it seems to be limited, coincidentally, along that line approximately by summer temperatures exceeding 20 degrees. It has gone further south during the Pleistocene. So, for example, during glacials, it's extended its range further south. It's found as fossil in the Great Salt Lake Basin in Utah. And there are some species that are extremely widely distributed. Quite a few that have northern hemisphere-wide distributions. Here's one that even gets into the southern hemisphere. This is Darwinia stevensoni. Very common in North America and Europe, but also found in South America, Australia, Southern Africa, Japan. We have to be able to try and capture these sorts of distributions. So here are the limitations of these regional databases. Regional proxy data sets may not capture the full ranges of the species that we're interested in climate space. Data sets collected by one person or group may be internally consistent in terms of sampling methods, taxonomy, positional accuracy, and so on, but they're more restricted in terms of geographical and climatic extent. And then the geographically more extensive databases, the literature-based ones, are more likely to cover species distributions, but they represent collections by many people over many years, so they're prone to taxonomic inconsistency, as well as poor locational precision and accuracy. And here's just one example. This is the sort of thing we're trying to sort out. This is from the Node database. This is an Austrian lake. These records are mapped into Google Earth. And we've got some records in the lake which are probably pretty accurate, but this little dandelion head, this cluster of records here, comes out of that point, which is somehow located halfway up a mountainside. And on checking, it turns out it belongs in that little lake down there. It's not a big positional error in terms of a Europe-wide database, but it could be a significant one, and we're spending a lot of time checking these things on Google Earth to make sure that the records actually appear where they say they should appear. So all of those things are why I need an RBD, a really big database. And my really big database is something called Omega. It's the ostracod metadatabase of environmental and geographical attributes. It's a project, an ongoing project that has been supported by, and it's contributing to something called BioFresh, which is an EU-funded international project building, or which has built now, a global information platform to put together freshwater databases of all kinds and make them available to everybody. And we're in the process of making Omega available to everybody via the BioFresh portal. And eventually we have plans to put it into something called Neotoma as well, which is a paleoecology database project in the US. And the Nanode database, the US one, is going into that as well at the moment. So to build and use Omega, and I hope that some of these comments here are kind of more widely applicable, we need, first of all, an agreement by database stewards, the people who own or manage the various regional databases, to contribute to the project, to provide their metadata. We're treating species names and site coordinates as both metadata and data, so that we can map the metadata, so that you can search on a map and find where you will find information about certain species, which databases to go to. We are not trying to merge regional databases to make a super database. We're leaving regional databases intact, if you like. It requires harmonization of taxonomies of the different data sets, and that is a real problem in freshwater ostracods. There are lots of arguments. We have to try and answer questions like, are all the species that are given the same names in different data sets really the same species? And are some that are perhaps listed under different names really the same species? And our focus at the moment is very much on the North American and European data sets. There do seem to be quite a number of species in common, but there are some that have gone under the same names that are not the same, and there's a lot of work to be done. We also need checking, correction and validation of geographical locations. I've already mentioned that example in the node database. And finally, we need some sort of standardization of climate data sets that are used for the calibrations, because people doing this sort of work with different regional databases have used different regional climate data sets, which may not be matched very precisely to the period of time in which the ostracods were collected, or they may be integrated over 30 years or 50 years or something like that. So we want some sort of standardization. So those are a few of the problems. Just to try and draw some concluding thoughts about this, a really big database is useful for a lot of things. It's useful for paleoenvironmental and paleoclimate reconstructions. It's useful for biogeographical studies or paleobiogeographical studies. It's potentially useful for biodiversity studies. And all of those things, all of the above, require taxonomic harmonization and spatial location of records. It's important to know where things occur. If you can't map the distributions to a reasonably high resolution, then the value of the database, to my mind, is extremely limited. I think that mere lists of names, taxonomic databases on their own, even if they're attributed to countries or regions, are simply inadequate for the kind of work, at least, that I'm interested in. And I want to make a couple of comments about just two examples. There seem to be a lot of so-called biodiversity databases on the internet now. A lot of them share the same data, at least as far as ostracods are concerned, and they share the same errors. According to Wikipedia, a biodiversity database, or databases, store taxonomic information which provides information on the biodiversity of a particular area or group of living organisms. I mean, we can argue about definitions and so on. But just to pick two examples, both of which I have been involved in at some stage. Fauna Europaea, a database of the scientific names and distribution of all living multicellular European land and freshwater animals. It does that, it lists them, but at least, certainly as far as the ostracods are concerned, it only does it at a country level resolution. So you can't make meaningful maps from it. The Worms database, the World Register of Marine Species, an authoritative and comprehensive list of names of marine organisms, including information on synonymy. Okay, so why does it include freshwater ostracods and fossil ostracods? Is this the best way of measuring biodiversity? And it includes an awful lot of junior synonyms and so on as well. I suspect I might get an answer to that question later on from another speaker. So, to conclude, the challenge of building a really big database, or the challenges, are time-consuming, but ultimately I think they're rewarding, and they're considerably more useful than the proliferation of web-based taxonomic accountancy that purports to audit biodiversity, but often lacks adequate spatial resolution for meaningful biogeographical studies. And I will leave you with that. Thank you.